All right, so quick, we're going to warm up with some ideas on how your calculator can help you graph piecewise functions. And we were just discussing in class that our calculators work in what's called Boolean algebra and logic. So if something comes out to a true statement, it calls it a 1. And if something comes out to a false statement, it calls it a 0. So what I want to do is I'm going to graph this piecewise function on our calculator. And we already kind of started that. So what I had the kids do is they write the first piece of the piecewise function into y1. But then they're going to divide it by an entire expression that represents the domain restriction. So the domain restriction was x is less than -5. So in the parentheses, you're going to type x, and then the less than symbol is buried in what's called the test menu. It's right above math. So second, math. And then you'll find, make sure you choose the right one, make sure you choose less than, not less than or equal to, so choose number 5. And then -5, type a negative symbol, not subtraction. So what's going to happen is my calculator is only going to graph things that are true. Think about this. Anything less than -5, it'll think is true, so it'll be dividing 4 by 1. 4 divided by 1 is going to keep spitting out a 4 every time, right? But if it's false, it's going to call it a 0. What happens when you take 4 and you divide it by the expression of 0? Your calculator blows up or something, right? It's undefined. It's undefined, and it won't graph it. So look at the graph. Woo! It graphed until it hit -5, and then it said, never mind, I'm undefined. And if you look at your table, it was giving you points up until you hit -5. And then it said error, 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 because it's not defined. The piece of that piecewise function stops at -5. So go to y2. Let's type in the second piece of our piecewise function, which I don't remember what it is. It's x to the 3rd power. And then you don't technically need parentheses because it's just a monomial, but maybe for good habit, because they're usually a little complicated, put x to the 3rd power in parentheses. If you didn't already do it, don't worry about it. But just the numerator means the function, the original piece of the piecewise function. And then you're going to divide it by the restriction. Now this is where it gets kind of weird. Your calculator does not have that sandwich understanding of like negative, I forgot what it is. Is it -2 to 2? Okay. So it won't understand -2 less than x less than 2. So we have to write them separately with the word and in between them. So the first piece of that sandwich says everything greater than or equal to -2. So you're going to type x, and then go back to that same test menu and pull up the greater than or equal to. It was greater than or equal to, wasn't it? -2. So I'm referring to this left side of the sandwich. It really says x is greater than or equal to -2. Then we have to pull up the word and. And you're like, where do they have and? So in that same menu, go back to test, but this time go over to the submenu called logic. There's an and. So choose that. Huh. And then x is, what's the other piece of the restriction? Less than or equal to 2, I think. So less than or equal would be number 6, and then 2. So now if you close that and then you go look at the graph, you're going to see 2 pieces of the piecewise function sitting there. And if you go to your table, you're going to see the red one, which coincides with the one we just graphed. You're going to see a bunch of errors where it doesn't exist, and then a bunch of ordered pairs that you could plot. So let's graph the final piece of the piecewise function, which was square root of x plus 3, was it? Okay, here you should put parentheses down, just, again, good habit. So square root of, did I have the right function? Is it x plus 3? Okay. And then get out of the radical and, get out of the radical and close your parentheses. And then hit a division, and then in your denominator put the restriction so it becomes undefined when it's not defined. I forgot what the restriction was. What was it? Greater than 2? Greater than 3, thank you. So x greater than, not equal to, or was it equal to? Okay, greater than 3. So when you hit graph, you see this beautiful piecewise function. The challenge for you guys would be to how to transfer it over to your paper if I'm asking you to graph it, which means you'd have to go visit your table and pull up points that coincide with what you want. Now here's the catch. I don't know about you, I found that very tedious. Like going to all these different submenus trying to find stuff. I mean, it's cool. Frankly, me, I'm quicker by hand. So I never use this, but I know it's kind of neat. The other catch is if you're in the middle of the test and you're like, hey, Brizzo, can you remind me how to do everything I'm supposed to do on my calculator? My answer is going to be no. So if you want to practice with this option, that's fine. Just make sure that on the test, in that moment, you're good to go. Oh, that poor baby. All right. Could you please find worksheet 8.5? What a weird title to a worksheet. Basically, we didn't have it in the packet, and we already labeled the packet, and then we had to sneak in another worksheet. Yeah, so this is a follow-up lesson to what we did yesterday. Yesterday I gave you a function, a piecewise function, and you had to graph it. Today I'm giving you the graph, and you got to come up with the function. So I think some good habits would appeal to you guys. Think about yesterday we marked up our boundary lines with a highlighter. I think you should probably do that again. So something happens here and here, so there's a restriction. Here's another restriction, here's another restriction, and then if you could, would you please put an arrow on the side of this little piece so it goes on for infinity? Give us a little variety in our notes. And we're going to have 3 pieces to this piecewise function, and I'm going to color code mine, of course, because that's me. And what I found out today is I really do need bifocals. I keep joking about it, but I think I secretly do. So tell me when I don't count something correctly, because I've been doing that a lot today. All right, there's our 3 pieces. Generally speaking, we go from the left and we work our way to the right. So if you don't mind, I'll stick with that. Let's talk about this blue piece. This little blue piece of the piecewise function. First, let's talk about the restrictions on its domain. So here's the origin, in case you're kind of lost on the graph. There's a restriction at -1, 2, 3, 4. Is that -5? And this is -1. So it starts at -5 and it stops at -1, I think. Again, guys, if I'm not counting right, let me know. Apparently I really, really need the bifocals. So on the restriction piece of this is what comes after the word if. So this blue piece only exists for x's that are between -5 and -1. So the way you write that is you write it as a sandwich. But why am I putting an equal to bar on the -5 and not on the -1? Because I have an open circle on the -1. Very good. So the blue function, while it exists between them, it only has a closed circle on the -5, not the -1. So I personally think the restrictions are one of the hardest parts of this problem. Coming up with the function shouldn't be too terrible. This blue piece is just a little horizontal line. What would the horizontal line equation look like? Y equals -2, yeah. So the body of the function is what you write down in the piecewise function, so you just do that. That's not too bad. So then, the next piece of the piecewise function, it starts and stops at, okay, I can do this. This is a 1, 2, 3, this is a 4. So it's sandwiched between 1 and 4, and this time it's got 2 closed circles on the red piece. So for the restriction, we'll say if your x's are between 1 and 4, but closed circles on both of them. So inequality with an equal to. So the red piece is a line. It's a piece of a line. And lines are in the form y equals mx plus b. So if you guys can figure out slope and you can figure out y-intercept, you should be able to give me the equation. And I don't want you actually calculating anything. You should just be using your graph. So your slope, just count for me, rise over run. What are you thinking? Me too. And then the y-intercept, that one you might have to use your imagination, but remember, you just found out your slope is 2. So if you could kind of back it up a little bit, where would it have crossed the y-axis? Oh, I'm glad you can see that. All right, so my function is 2x minus 4. That wasn't too bad. All right, green piece, we're back to one of those easy horizontal lines. But the restriction on it is only for x's that are greater than 4. And notice I said greater than 4. Why did I not say greater than or equal to 4? Because it's got an open circle, so it can't have an equal to. And what height are we looking at? 1, 2, is that 5? All right, cool. So this is the line y equals 5, but it's just a piece of it. That's why we have that piecewise function look. So what do you think? Not too bad? This is a good synthesis moment in math. We do a problem one direction, and then we come back the next day and we do it the other direction. Now you're really going to be masters of the piecewise function. Oh, and then she throws this at us. Okay, so my vow to you is that if I give you a not-so-traditional looking graph, so something nonlinear essentially, they're going to be incredibly basic functions. So what I mean by that is you won't have to calculate the a value like we did on the last test. You won't have to do some crazy math to figure out if it's secretly stretched a weird way. So your a values are going to either be 1 or -1, depending on the direction in which they open, or if there's a reflection. They will be transformed right and left and up and down, but no stretching will occur on the weird pieces of the piecewise function. So this first piece of the piecewise function, it's not the color I was looking for. There we go, blue. Give me a name for this graph. What is it? It's a parabola. Yeah, it's a quadratic function. So let's just assume, because we think my teacher's not trying to trick me, that whatever this point is, that is my vertex, which it is. And let's assume that the a value is, you guys tell me, is this going to have a positive a value or a negative a value? If it's opening up, it's a positive a value. So we'll just assume that the a value is a 1 here. Oh, I didn't do any highlighting though. Let me mark up my boundary lines. All right, so we added arrows to the we added arrows to the ends. Make sure you add arrows as well. Looks like something happens at, here's the origin. So something happens here at -2, and something happens here at 2. All right, blue piece of the piecewise function. It is a parabola whose vertex has been shifted 1, 2, 3, 4 units to the left. What does that look like? X plus 4 quantity squared. It has not been shifted up or down any, so it's still at 0. You can put a +0 here if you want. I'm not going to. So the body of the function for that blue piece is x plus 4 quantity squared. Oops, I forgot to do the restriction. This only exists for x's that are less than -2. And should I put an equal to or not? Yes, this time I should put an equal to, because it's got a closed circle on the -2. All right, the next piece of my piecewise function is a good old line. It only exists between x's of -2 and 2. And this time, there's open circles on each of the endpoints. So when you set up your sandwich, don't put bars underneath the inequalities. All right, remember a line. You need to figure out the y-intercept and you need to figure out the slope. I think you can count and tell me what your slope is. Up 1/2? And then can you see, I think you can see where it crosses the y-axis. Yeah. So my equation is just that, 1/2 x plus 3. And then the green piece starts at starts at 2 and then continues on forever. Oh man. Can you at least tell me that it is a line? Can you tell me what the slope is? Yeah, I'm with you. I think it's a -2/1, so -2. And then if you aren't sure where it crosses the y-axis, which me neither, I'm going to have to back it up a little bit. So go the other direction, up to left 1, up to left 1. It would have crossed right there. So where's the y-intercept? Yeah, it's at +10. So your function for the green piece is -2x plus 10. But this guy only exists for x's that are greater than or equal to 2. Very good. It's got an equal to on it this time because it's a filled in circle. So that's a hoot. Let's do some more of that. Flip the page over. I got 2 more for you. Ooh. Okay. So we got some boundaries. Let's do a little highlighting. Help your old 80 eyes. You don't have old 80 eyes. That's just me. You know, I'm telling you, all first hour I kept doing this, and I don't think there's a single question where I didn't make a mistake. All right. Ooh, I don't know why that went yellow. Can you put an arrow on the end of this guy? Make this go on forever. And this is the origin right here. So all my boundary line, my restrictions, they're happening, let's see, this guy's at a 2. This is at a -1. This is at a -3. And this one, 4, 5, 6. Is that -7? Hope. We'll go with it. All right. Let's talk about our first piece to the piecewise function. It starts here, and it ends here. So it's one of those easy functions. So let's set up our sandwich inequality. It's all your values between -7 and 3. So I'm going to set up a sandwich. Can you tell me how to use my inequalities, though? On the -7, what kind of an inequality are we doing here? Less than or equal to. So -7 less than or equal to x. And then on the 3, sorry, -3? Just a less than. Very good, because it's got an open circle. But the function itself, this red piece, is just a horizontal line up here at y equals 1, 2, 3, is it 4? Okay, cool. So I'm going to put down the body only, so 4. Let's talk about this middle piece. It is a line. Oh, man. It is a line. It stretches between, what is that, -1 and 2? So again, we're sandwiched. It's got a closed circle on the -1 and an open circle on the 2. And if you could figure out the slope and the y-intercept, you'll be in business.
Y-intercept is 2.
Yep.
Slope, I don't know.
Feeling a 1 on the slope. So is the equation x plus 2? Okay. Easy peasy lemon squeezy. And now for the weird one. Anybody think they remember this guy? Who's the parent function to this?
It's a square root.
It is a square root graph. Now, let's just assume my teacher's not trying to be tricky, and this is the origination point of the square root function. So how has it been shifted? Over to the right 2. What would that look like in my function then?
X.
Very good. Inside the radical and x minus 2. So that would be a square root who's been shifted right 2. Good, good.
Wait, why would it be minus?
Remember the function is opposites with the h's. It's x minus h. So, yeah, they're weird ones. Yes, Daniel?
If that were on a test and there was actually a shift to it, you would make sure that it's obvious.
Yes.
The shift.
Yes. And actually, I'm going to be fully transparent. I think we just gave you lines on the test.
Oh,
Isn't that wonderful? What nice ladies.
Oh my gosh.
High fives all around, teachers. Good job. I should have saved that for like the day before the test, though, because now you still need to practice it, though, because who knows what we'll do in the future. All right, so this only exists for x's that, oh, what's wrong with my colors today? It's me. All right, x's that are greater than 2. Why did I not put an equal to bar on that? Open circle. Very good. All right, one more for fun. Oh. Okay. This feels like the hardest one. Put an arrow on the end of this last piece here. Everybody else starts and stops. So help me out here with where my restriction and my boundary lines are going to be. Oh, that was not straight. Okay, so here's the origin. That was supposed to be at 2. This is at -1. 2, 3, 4. Is this at -5? Okay, cool. Whew. Colors. I need them. Anybody think they know what parent function this is related to?
Square root.
It is a square root. Yeah, it's a weird one, though. Let's assume that this guy right here is the start of it. How is it shifted?
Left.
Yes, so the function says x plus 5 because it's shifted to the left. Very good. But this function only exists for x's between -5 and -1, so you got to show me your sandwich inequality, and there's open circles on both. So between -5 and -1 in that little sandwich notation. And then we got this little line, which we know Okay, so we know lines are in the form mx plus b. It's the easiest form we have. Can you tell what the slope and the y-intercept are from the graph? I can't read. I drew stupid. Okay. Is it a slope of 3?
Yeah.
Okay. And then you said it crossed at +1? Cool. All right, there we go. 3x plus 1. Only for x's between -1 and 2. This time we have 2 filled in circles, so your sandwich should have inequalities with equal to bars under them. So -1 less than or equal to x less than or equal to 2. And then this guy. Who do you think that's a relative of? It's a quadratic. Good. And why is it negative, Adam? Very good. Because it's been reflected. Very good. So there's a negative in front. Let's assume this guy is the vertex. How would you indicate that on my function then? If it's been shifted to the right 2, what would that look like? X minus 2 quantity squared, and then it's been shifted up. I can't read. Is that 4? So up 4 would be like this. So I don't know why I wrote it like halfway in the problem. Let's go over here. We just decided that the quadratic was reflected and then shifted right 2 and up 4. That function only exists for x's that are greater than 2. Very nice. So we're really, when we ask you to create a piecewise function and it's nonlinear, I'm asking you to incorporate your knowledge of the rigid transformations. Things like shifting right and left and up and down. Might throw a reflection in there to get crazy. So you guys have enough information in your brain now where you can finish the piecewise packet. That's your official assignment for tonight, is to finish the piecewise packet. We are almost done with the homework check. We have one more assignment coming to you tomorrow, and then we're done. So you need to do a little inventory and think, okay, how far into the homework check am I? Because you just told yourself how much homework you're going to have this weekend. Which hopefully the answer is not a lot.
What does it do?
Tuesday. Okay? It's a big homework check. I'm going to be honest. You do. You do. You can turn it in Monday if it's done. You're welcome to. I love early homework checks. But Mrs. Hofbauer and I were concerned that some of us haven't practiced graph analysis as much as we should have. So what we're going to do is we have this little exit ticket. We're going to do one side of it together to refresh your memory, and then you're going to flip around and do the back side on your own. I'm going to pause the video while I get these passed out, and then we'll join back up in a moment. All right, so we're going to do this problem together. We are going to be estimating only, which means I will give you a little grace if you estimate a little differently from your counterparts who are going to give me answers. But there's some key things we're going to be looking at. And remember, these are the questions where I did a lot of coloring and highlighting. So if you still have those highlighters handy and pens, this might be a good moment. All right, let's start with zeros. I need to know, and it will be a bit of an estimation on some cases, where the zeros are for this function. So I'm looking for where your function crosses the x-axis. So, anyone see a 0? Negative 2.3 comma 0 sounds wonderful. I'll take that. Where's another x-intercept? 1, 0. Nice. Where's another x-intercept? Love it. 4.40, 4.50. It's an estimation, so I will take whatever you just told me. The y-intercept would be where your function crosses the y-axis. Now, careful, this y-axis is counting by tens. So you're feeling 11? Okay. So 0, 11 for a y-intercept. Again, it's an estimation. On the test, I believe we give you the function, and you have to find all this on the calculator. So you'll have actual answers that you know are right. Estimation, please, for where you think this maximum occurs. I'll accept that, except I'll call it negative 1. And then what about this minimum here? Yes. 3, would you say on negative 15? I'll take that. And this is where I bust up my highlighters. Do you remember what I highlight here? Yes. Very carefully, I'm going to highlight the x values for my minimum and my maximum that you just found. And I'm going to highlight them on my graph and in my problem over here, because when I go to give my teacher increasing and decreasing intervals, I got to make sure that I'm only using those x values and infinities. All right, time to talk about roller coasters. This first piece of the function, is it considered an increasing or decreasing roller coaster track? Increasing. So when is it increasing? Negative infinity to negative 1. Close it with a parenthesis. Then your track turns around and it becomes a decreasing roller coaster track. From when to when? Very nice. Negative 1 to 3. But then it turns again, and now you have an increasing interval. From when to when? Very good. 3 and then forever. So, you know me, I like colors in my math, so you're always going to see this glorious art project at the end of it. This is good for me, right? Okay, inflection point. This is going to be an estimation, but I trained you guys to kind of find the halfway point between your maximum and minimum. So that -1 and that 3 that you were using, if you could find what is exactly in the middle of that, that would be very helpful. What'd you get? That's a uno, which is probably where most kids would have estimated the inflection point to be anyways. You're feeling like right there is the inflection point. So I'm going to call it 1, 0. Mrs. Hoffbauer's kids literally only estimate it, like they look and they go, it feels like it's at 1, 0. And that's fine for us as well. I like to give you guys a process in case you're worried that you have to find something in particular. So here, I don't want to like add more to this picture because it's got a lot going on. So I'm going to give myself like a quick little sketch that kind of looks like the function. And the only thing I'm going to label on it is that inflection point. And actually all I really care about is the x value of that inflection point. Because when I ask you about concavity, this is the smiley face, frowny face stuff. So this first piece right here, what do you guys think you would call that? That's concave down. Very good. Which means when it turns, now you're looking at concave up. That means it looks like a smiley face piece, right? So it is concave up from when to when? So concave up would be from the other one, so 1 to infinity. And then concave down was the one that you were telling me, thank you, -infinity to 1. And then why not give you an end behavior question? Okay, me. I always do end behavior the same way so I don't confuse my dyslexia. I always give the left behavior first. How do I indicate that I'm looking at the left behavior? What do I write down? X goes to the left as x goes to -infinity. So if you look on the left side of your function, where is your function traveling? Down. How do we say down, Fancy? -infinity. Very good. And then that means I have to now give the right side for end behavior, which is x goes to positive infinity. And where is it going on the right side? Up, up, up to infinity. Very good. All right, so what you're going to do now as an exit ticket, you're going to flip that page over. Sweet Hoffbauer, I think she labeled points for you. She's so nice. She labeled a few things for you. She called this, what did she call this? This minimum right here, I think she labeled at -1.3, comma, -13. She labeled this guy as a -0.2 in case you were hemming and hawing over that one. And then this maximum here, she calls a 1.9 and a 38. All right, for you to finish. Good luck.